So we ended up doing a solubility test in the lab, okay? And we found that for the most part, most of the things that we tested were soluble. I know a few of you watched the video there, okay, of the results, okay, and obviously go right ahead and do that. That's why I put it there. But it was probably easier to see the results of the solubility test in the big dish than it was kind of in the small one. So it might not be a bad idea to look at that, but we could see that when things were starting to dissolve, there were noticeable changes that went on. Okay, for some of the things it meant that the temperature changed. For some of the things it meant that the crystals shrank or got kind of more rounded off, changed shape or whatever. Okay, sometimes the solution assumed the color of the crystals and such. Okay, but was everything equally soluble? No. Okay, solubility is a physical property, and everything is got a different degree to which it will dissolve in not only water but other things as well. Typically, we measure solubility as how much it dissolves in water, okay? But I mean, solubility could be anything dissolving in anything else, all right? It could be, let's say, paint being able to dissolve in gasoline, whereas maybe not so much in water. I mean, latex paint would, but okay, if you had an oil-based paint and you get that or a stain on your hands, right, it doesn't come off with soap and water unless you scrub for hours, okay? But if you put it in paint thinner or gasoline or something like that, it comes right off, okay? It's not soluble in water, but it's soluble in other solvents, okay? A solvent is anything that can dissolve something else. So what we're gonna go over today is just kind of what solubility is, some terminology, okay? So vocabulary, things like that to do with it, and looking also at how to use your solubility chart that is on the back of your periodic table. All right, so like we said, learn the terminology related to solubility, understand what's meant by the term polar molecule. We're also going to talk about the nature of water here, okay? Remember how we said that every time there's a rule in chemistry, it seems like water's the exception? Today we're going to talk about why, okay? It has to do with the structure of the water molecule, okay? And because it's a polar molecule, water has many important and unique properties that make life on Earth possible. Okay, so some substances dissolve easily, okay? Some don't. Okay, the degree to which they dissolve is called solubility. Okay, so that's your first term. The term solubility means the degree to which something dissolves in something else. Okay, and like it says here, chart in your text, it shouldn't say text, it should say on your periodic table. Okay, so that's on your periodic table for a list of ions and their solubility. We'll go over that in a little bit. Okay, a substance is said to be insoluble if it will not dissolve in something else, right? So yesterday you had for sure one material that was completely insoluble in the lab. It did nothing but basically float on top of the water, okay? And it just wouldn't, no matter how much you stirred it or whatever, it wouldn't dissolve, right? So that material was insoluble. Now here's one of the problems with the English language. Insoluble means it won't dissolve. Inflammable means it will catch on fire. I don't get it. Again, I'm not an English major, but that seems to not make sense to me. Okay? Insoluble means it won't dissolve, but inflammable means it's highly flammable. Wow. Well, inflammable also means flammable, apparently. Yeah, weird stuff. Okay. All right, if a substance remains insoluble and in a solid form, we often refer to it as a precipitate, especially if it was formed as the result of a chemical reaction. Okay? Sometimes I can mix two clear solutions together and suddenly a solid will form. Now, I don't mean like a solid chunk, but like a powdery solid will form, and it typically kind of falls out of the solution. So it forms and then falls to the bottom of the container, like snow, hence the name precipitate. Tends to fall out of the solution. Okay, that's what the term precipitate means. Okay, it means to fall out of something, right? Okay, everybody okay with those terms? Right, those are terms that I'm going to use fairly often. Okay, so a precipitate is a solid, okay, that forms as a result of a chemical reaction, and it's insoluble. All right, solution. Any mixture containing a solute dissolved in a solvent. Okay, so if I have something dissolved in something else, I have a solution. So the stuff, many of the things you created yesterday were solutions. right? We added water to them and they dissolved, and then we were able to take the conductivity of the solution. So we had a solute, that's the thing that's getting dissolved in a solvent. The solvent is the thing doing the dissolving, right? We often refer to water as the universal solvent because it can dissolve pretty much anything, okay, with a few exceptions, obviously. All right. Now, if I get something to totally dissolve, we often call that a homogeneous or homogeneous, however you want to pronounce it, either way is fine. Okay, a homogeneous mixture. Okay, what does the word homogeneous mean? The same throughout, yes. Okay, the same throughout is what homogeneous means. That the prefix homo means one. Okay, and that's what it means. So genius means like mixture. Okay, so that would be one part. All right, you can remember that because right, other terms have the prefix homo on them as well. Okay, like if someone is homosexual, they have that couple only has one gender in it. Everybody follow the term. That's what the prefix homo means is one. All right, just so everyone is clear on that. You won't forget it now either. Okay, I use an example like that, you won't forget it. All right. And then if I have, so this one here on the left would be considered a homogeneous mixture. It only has one visible part, okay? There's nothing floating on the top. There's no particles that are obviously not dissolved floating in there, okay? Anything like that. There's one visible part. But this one on the right has two visible parts. We can see that there's kind of this yellowy liquid, and then there's this kind of red solid at the bottom. There's more than one visible part to this, which means something didn't dissolve. Okay, in that case, we have what is called a heterogeneous mixture. Okay, hetero means many. All right, so this has many parts. So it's not a solution. Right? We sometimes call a heterogeneous mixture a mechanical mixture. Right? If I was to, let's say, take a bunch of iron filings and sand and put them in a container and shake them up, okay, it's not really a solution, right? They haven't dissolved in each other, but they're mixed together. But they're mixed together mechanically. I could still easily separate them based on their physical properties, right? If I stuck a magnet in there, right, I could pull all the iron filings out and leave the sand behind. Everybody follow? Okay, so mechanical mixture there. Okay, oil and water would also be a mechanical mixture. I mean, if you stir oil and water, you can kind of keep the oil from going to the top, right? You can kind of get it to be inside, but it's not dissolved. It's just mechanically mixed in. If you leave it after stirring it, it'll eventually re-separate. Okay, so that would be anything that's a mechanical mixture there. Okay, so a solute is the substance that's being dissolved, right? We talked about that already. So solute is the substance being dissolved. So if I'm making coffee in the morning and I'm putting sugar in it, the sugar is the solute, okay? Coffee is the solvent. If, well, I mean, if it will all dissolve, regardless of how long it takes, it's soluble, right? In the end, it's not about so much how long it takes, it's about whether or not you can get it to dissolve and how much will go in. Typically, things that are highly soluble also dissolve quickly, right? Typically. It's typically measured in how many grams per liter or moles per liter you can put in something. Moles is another way of measuring the amount of something, right? So that's usually how we measure concentration. So the higher the concentration I can create before it's saturated would be the solubility. On your lab, I mean, I would say more than just yes or no. I would kind of give it a bit of a description. Like you could say, the crystal shrank but didn't disappear completely. But that means that it is soluble because we have to consider that we didn't have a whole lot of water, right? And that's why it's probably a good idea to watch the video of the larger sample sizes because I got those to dissolve like basically all of them that were soluble. I essentially got it all to go away. Okay, so you can have a look at that just to kind of review if you're unsure of any of your solubility tests. Kind of both. Yeah, you kind of measure solubility. I mean, it's referred to more by the solute because the solvent is usually water. But yeah, it's usually how many grams of the solute can go into 1 liter of the solvent. That's why the units are moles per liter or grams per liter. We're basically never going to use those units for anything. We just need to understand what solubility means, okay, and whether something is soluble or not. We're not going to look at concentrations. You'll do that in Chem 20. In fact, it's one of the first things you do. Okay, so if we have salt and water, okay, salt is the solute, water is the solvent. Okay, if you make hot chocolate, okay, the powdered mix is the solute, and the water is the solvent. Okay, and so on and so on. You know, our paint example, paint and gasoline, or paint and Varsol, paint thinner, whatever. Okay, the paint is the solute, and the paint thinner is the solvent. That's why we typically refer to anything that can clean something up as a solvent. Okay, like Mr. Clean is a solvent. Right? It helps water to dissolve other things. It essentially makes it a better solvent, okay, and allows it to dissolve stuff that water wouldn't dissolve very well on its own, like hard water scales, soap scum, right, stuff like that that might be on your shower. Okay, Mr. Clean or any other solvent would help you to dissolve that better. Right? If you just sat there and scrubbed with a wet brush, you would be sitting there scrubbing for quite a while. Okay? Water is a decent solvent, but it's a lot of elbow grease if all you're using is water. And that's why we use other things. Okay, questions there so far? Okay, what are some things that can affect solubility? Temperature is one of them. Okay, so okay, temperature. Okay, in terms of how quickly I could get it to dissolve, surface area would be a factor. In the end, it's not something like eventually I'd be able to get something to dissolve, whether it was one big chunk or powder. It'd just be how fast. But in the end, the solubility would be considered the same. But yeah, you're right. I can get something to dissolve much faster if it's in small crystals as opposed to a big chunk. Okay, like if you're making coffee and use a spoon with sugar as opposed to a cube, okay, it's way easier to get the spoonful to dissolve. Well, the amount that you could get in is this, right? So it's not so much affected by it as it is it. Yeah? No, I mean bigger volume of water. I mean, like, yes, I used a bigger sample tray. I used about the same, I used a little bit more of the sample, but I used a lot more water when I did, and that's what made me able to dissolve it better than you guys. Agitation, yeah. Okay, just pouring sugar into something is not going to make it dissolve very fast. But if you get the particles moving, okay, then they, you kind of find the spaces in between the particles a lot faster. Okay, so agitation certainly would do that. Yeah, you can put catalysts in that they typically make reactions go faster, but there are some that could improve solubility as well. Okay, so there are things that can affect solubility, okay, which is why if we were looking at a number, like expressing solubility as a number for a material, it has to be at these conditions, which we usually call standard conditions, which would be 20 degrees Celsius, 1 atmosphere of atmospheric pressure, because atmospheric pressure can also affect solubility, okay, and with no agitation. Okay, so like I said, there are things that can affect it. So if we're going to have a standard measure, all the other conditions have to be the same. All right, so a precipitate is any solid that's produced in a reaction and will not dissolve in the solution. All right, and I'll show you a quick video of that here, and then we'll talk about the disgusting picture underneath. Okay, so some things are soluble, some things are not. As we move towards being able to replace natural substances with artificial ones, we find that while, let's say, like if we're talking about food items here, we find that sometimes we're replacing natural items with artificial ones, and we're changing not so much the taste, although a lot of people would argue that we are, okay, but we're also altering the properties of the overall end product. Okay, back when Twinkies first came out, what would you suppose they were made with? Okay, so they had flour in them. Okay, what else? What makes them yellow? What made them yellow? Okay, we're making cake here. Like, what kind of? I mean, that's what a Twinkie is. Essentially cake, right? So you got like eggs, oils, okay, things like that. Like lard would have been an ingredient. You don't want to use that anymore because it causes elevated cholesterol and heart attacks and stuff like that. So these natural ingredients like eggs and lard and milk and flour and stuff like that, the problem with using them was Twinkies didn't last very long. They would spoil quickly because they were full of natural ingredients. Well, Hostess, the company that makes Twinkies, doesn't want to ship out a whole bunch of Twinkies and have them all go bad before they're sold. So they started doing is finding replacements, artificial replacements that, let's say, bacteria or mold and things like that wouldn't eat, but would still taste the same and result in their product lasting longer on the shelf and increasing the likelihood it would be purchased before it's spoiled. Right? So from a business perspective, this is what they're doing. So they start finding things that are like the natural ingredients. Okay, so they replace the eggs with these like agar and amalgam kind of semi-artificial proteins. They replaced milk with like powdered milk or other kind of milk substitutes. Okay, they replaced the lard with other types of oil that are less, let's say, not saturated fats but unsaturated. Okay, and things like that. Now, they got to the point where they had basically replaced everything, but they had one problem. In replacing all of the stuff, they had a Twinkie, but it was gray. It looked like it was the color of like drywall, okay? Which people found unappetizing, okay? Twinkies are supposed to be yellow because what made them yellow was the natural ingredients, specifically the eggs. Okay, the egg yolk that was used to make the batter. Well, without the eggs being in there, they had this kind of grayish color, which wasn't appetizing. So they didn't sell very well. So instead, they added in yellow dye number 5, which is banned in many, many countries around the world because it is a known carcinogen. Okay, it means it causes cancer. Okay, but it's yellow, and it made Twinkies look like the old Twinkies. Okay. Think about that. I'm not discouraging you from eating Twinkies. Anything in small amounts is fine. If you're eating Twinkies 5 a day, that's not the best dietary choice for you. Okay? But in the end, what's happened is they took a Twinkie, which if you put in water, would have just gotten soggy and sponge-like. They've taken that natural thing and they've turned it into something that is soluble in water. Okay? If you take a Twinkie out of the package and put it in a cup of water, over the course of an hour, it will become a semi-dissolved mush. Yeah. So if you break your jaw, you could eat Twinkies. You just put them in a little bit of water and you can drink them down in about an hour. I'm not saying it's going to taste as good, but it's, yeah. A Twinkie is soluble in water because it's no longer filled with all the natural ingredients it used to have. Okay. So this is what you get after about an hour. Okay. Like you pour it out and it's not like wet cake. It's like pretty much dissolved. Yeah. I know it looks like a pool of vomit and it's a bit disgusting, but yeah. Hey, you can also see here that this Twinkie here that's been in for just a little while, the yellow dye number 5 is highly soluble in water. You can already see that it's essentially been taken out of the Twinkie and the Twinkie's turning almost like a grayish white color. Okay? But the water is turning yellow because it's that soluble in water. Okay? All right. So yeah, keep that in mind. Other things, what other kind of things do they add to foods now to keep them good longer? Oh, yeah, so we might have artificial sweeteners because artificial sweeteners like aspartame, stevia, Splenda, things like that, they don't have any caloric value, so they're not food, right? That makes, I can eat a Twinkie that's sweetened with one of those and not have to worry about gaining weight because it doesn't have any calories in it. I also don't have to worry about bacteria or mold wanting to grow on it because it's not food anymore. I know it looks like food, but it's not natural food. It doesn't have any calories, so it does them no good to grow on it because they get nothing from it. Yeah, and preservatives. Now, in some foods, it's lots of salts and sodium and stuff like that because if you make something really salty, then it's harder for bacteria and mold to grow on it. That's the idea behind beef jerky. Okay, if you've ever made beef jerky, you essentially take the meat and you kind of work salt and curing salt and stuff like that and the spices and whatever else into the meat, and then you let it dry. Okay, and the salt will keep stuff from growing on it. But you can also add other things called preservatives, okay, that are not necessarily salts. Like, for example, one of the preservatives used in Twinkies is also used in mortician's fluid. It's the stuff they inject into dead bodies to keep them from smelling before the funeral. Okay? Yeah. It does a great job of preventing mold and bacterial growth. But it's probably not like good for you either. I mean, again, the amount of it that would be in one Twinkie, not going to kill you. The amount of it that would be in 20 Twinkies a day, yeah, probably not so good, right? They have a question. Yeah, so there'd be different types of fats, depending again when we switch the oils, right? We would have the natural kind of saturated fats versus the non-saturated fats, like shortening or vegetable oil would have non-saturated, whereas lard is a saturated fat. Okay. Oh yeah, that's the issue. It's not. I mean, again, everything in moderation. If I have one Twinkie, it's not going to kill me, right? But if I eat a lot of them, or I eat a lot of heavily processed foods, then that's probably not good for me because I'm taking in a lot of other chemicals. No, I'm not saying like I'm not one of these people that I won't eat anything that casts a shadow. Okay, like I'm not like that. Okay, I eat lots of crap too. But you just have to understand that when you do that, you are choosing to eat stuff that's probably in large amounts not all that good for you. Yeah. Yes. Sodium and sulfites are the ones, the salty types of preservatives, yeah, that really do a good job of inhibiting bacterial and mold growth. Yeah, they all have really technical names. Sounds yummy. But there are lots of preservatives and chemicals, and many of them are soluble in water. That's how you can get them into the food, right? You mix them in during the preparation process, then you cook the food or whatever, and they're in there now because they were able to dissolve in the fluids or whatever that you made in the food. Okay, this chart is on the back of your periodic table. And so if you can take that out, you'll see a chart that looks like this one. Okay, so this is the solubility of some common ionic compounds in water at 298.15 Kelvin. All right, you don't have to worry about that. It's just, like we said, we have to have a standard temperature for everything to have a fair comparison. Okay, we would also say at 1 atmosphere with no agitation, blah, blah, blah. Okay, here's how this chart works. Okay, if I want to decide whether a compound is soluble or not soluble, I've got to look up the two parts on here. Okay, so along the top row, you'll see a bunch of ions. Okay, so in this first column here, we've got like hydrogen and sodium, we've got ammonium nitrate, okay, we've got acetate and chlorate and all that kind of stuff. Chlorite, all of that is in here, right? And these things here, it says that they are very soluble with most things. I know that's not great, okay? It doesn't seem very scientific to have a word like most on a table, but okay, in this case it works. And then down below is a list of the things that it would be slightly or not soluble with. If it says slightly soluble, it really essentially means it's not soluble. It would probably form a precipitate, okay? So let's say that I was told I had this particular compound here. Magnesium fluoride. And I was asked to find out whether this is soluble or not soluble in water, right? So I look up fluorine on the top here. Here it is. Okay, so fluorine is right here. It says that fluorine is soluble with most things. Well, that's not very helpful in this case because I'm trying to find out whether this is soluble or not. So if it says most, I have to look down below into the row that is things it is not soluble with. Okay, and I see lithium and magnesium. So this stuff would be not soluble, or slightly. We'd basically just say not soluble. Okay? Magnesium fluoride would not be soluble in water. In other words, it would create a precipitate, okay, in water. All right, let's try this one here. Ammonium phosphate. I want to find out if ammonium phosphate is soluble in water. All right, so same procedure. I go over until I find phosphate, which is right here. And phosphate is soluble with these things. And ammonium is there. So ammonium phosphate would be soluble in water. Okay, whereas basically everything else is not. Okay, with the exception of these other three things. Usually it's the second one, yes. Yeah, usually you find the negatively charged ion up here. There's a few exceptions, okay? But usually you're looking for the negatively charged ion on the top row and then seeing here's what it's with. And again, these are all ionic compounds, okay? We don't have a chart for molecular because molecular compounds we already know are all generally less soluble anyway, okay? So this only deals with ionic compounds. Everybody kind of follow how that works? Okay. Sorry, I wanted you guys to try a couple of other. Okay, I had them there. I want you guys to tell me for those 8. Look them up on your chart. Just write. So write them down and just write beside them S or N. Okay, not soluble or soluble. And then we'll go over them here in a minute. All right. So first one here we got lithium fluoride. Okay, so we go up top. We look for fluorine. Okay, so it's right here. Okay, and it says it's soluble with most things, but we see that lithium is in the second row. Okay, that's the not soluble row, right? So this compound would be not soluble. Whoops, I just erased everything. That was not a good idea. Yeah, that's pretty much all you have to do. I know, but I said already, slightly soluble really means not soluble. Everything is soluble to some extent, right? We can't, I mean, if we say not soluble, we're not saying none of it will dissolve, but very little, and we're going to get a precipitate. In other words, the solution will be saturated almost immediately. Okay, does everyone follow what I mean by saturated? Okay, it's another term we haven't got to yet, but saturated means I can't get any more to dissolve. Okay, it's how I make Kool-Aid. Right? I add water, I put water in, then I add sugar until I get a nice layer of sugar on the bottom of the container. Okay? It is a saturated solution because no more sugar will dissolve. Yeah? All right, second one, we got sodium sulfate. So we look for sulfate, okay? Sulfate is right here, and it says that it is soluble with most things, but not these things. Well, I don't see sodium in amongst that group. That must mean that sodium is part of most, and as a result, this compound is soluble. Okay, number 3, we got ammonium nitrate. Okay, nitrate here, soluble with most things except for these really complex, weird, rare things. Okay, for all intents and purposes, anything that has nitrate attached to it is soluble in water. Nitrates are highly soluble. Okay. All right, silver chloride. All right, so chlorine is right here. Okay, it says it's soluble with most things, but I see that silver is listed there in the second row, so silver chloride is not soluble. Okay, lead 2 iodide. Right, iodine is in that same column with chlorine and bromine. It says it's soluble with most things, but I can see that lead 2 plus is listed there, so it's not soluble. Okay, hydrogen sulfide. Okay, so I see sulfide here near the end. Okay, and H is listed there in the first row, so that stuff is soluble. And then we've got potassium phosphate. So I look for phosphate, okay, and phosphate is right here, right? It says it's soluble with most things, okay? Whoops, sorry. It says it's soluble with K. So this one would be soluble. And then last one, we've got mercury 2 chloride. So chlorine, again, is right here, soluble with most things, but I can see that mercury 2 plus is here, as well as this mercury, but this is the mercury that it was involved, okay? Hg2 plus, so that stuff is not soluble. All right, everybody follow how that chart works? All right, pardon me? 8, yeah. All right. That's, I mean, you're going to use that solubility chart quite a bit more in Chem 20 because we'll be concerned with the states of matter in chemical reactions, which we're not concerned about in Science 10. But when you write out reactions in Chem 20, you actually have to write whether they're solid, liquid, gas, or aqueous, which means dissolved in solution. So if something is not soluble, it'll be a precipitate, which means it'll be a solid. So you would write S beside it for solid. Whereas if something was soluble, you would write AQ beside it because it's aqueous, it's dissolved in water, right? So that's the reason we need to teach you guys how this thing works, okay? All right, we'll also be using this as part of our reactions lab because in our reactions lab, a few of our reactions will produce precipitates, and then we'll have to identify what those precipitates are, okay? And that can be done using this chart. All right, so next thing we got to talk about here is the nature of water, okay? Water obviously behaves differently, excuse me, than a lot of other things. So what we got to look at is why. Okay. Now, in a molecular compound, and water is a molecular compound. I know that seems weird because I told you hydrogen's listed first. Hydrogen's acting as a metal, and it's ionic, except that if that was the case for water, written as H2O, then water would be an acid. Is water an acid? No. Okay, so water, again, kind of behaves oddly. Okay, now here's the structure of water. We got the two hydrogens up top, okay, and we got the oxygen atom down below. Right? They are sharing electrons because it's a molecular compound and they have a covalent bond where they share the electrons. But here's the thing. Covalent bonds aren't all exactly like we talked about before. We said, oh, well, they're all happy and they're sharing their electrons and everything's hunky-dory, except that sharing stuff is never perfectly equal. Okay, and it's also the case here with water. Okay, these electrons are not shared equally between the hydrogen atom and the oxygen atom. Oxygen gets to share them more often. Okay, that means that the electrons end up hanging out near oxygen more than they hang out near the hydrogen atoms. Right, so the orbit of this electron isn't so much circular like this as it is elliptical like this. Okay, so oxygen holds onto electrons way more tightly than does hydrogen. If you look on your periodic table, so flip it back over, not to the solubility side, okay, but you'll see there's a little key at the top here, and iron is the one they've chosen for the key, and it says there's the atomic number, which for iron is 26, and then there's a number underneath it that says electronegativity. Okay, electronegativity is how hard an atom holds on to its electrons. The higher the number, the harder it holds on to electrons. All right, so if we look at oxygen, oxygen's electronegativity is 3.4. Hydrogen's electronegativity is 2.2. Okay, so when they bond together and have a covalent bond, the electrons end up being near oxygen more because oxygen can hold them more tightly than hydrogen can. Okay, so what ends up happening is we have electrons, more electrons down here at the bottom of the atom than we have up top. And you can kind of see that in the way that this diagram is drawn. Okay, we can see that the electrons are here, and there's these two, well, in a hydrogen atom, this is just a proton, right? The nucleus has a proton in it, and that's it. So there's a proton exposed, and then there's all these electrons down below. So what ends up happening is the top of the molecule ends up being positive, and the bottom of the molecule ends up being negative. All right, it's not a charged particle per se. It isn't, because the electrons are being shared. But because the electrons end up down around oxygen more often, this end of the compound or molecule is a little bit more negative than the top. Okay, this is what's going to allow water to do some of the strange things that water does. Because the ends of it have sort of charges, we call it polar, just like the world is polar. We got a north pole and a south pole. Okay, well, on a water molecule, we got a positive pole, another positive pole, and negative poles down below. Question? They can, but they don't, and it has to do with, again, the repulsion of the electrons, where they get, where they end up when they're being shared, and so certain shapes arise. It's something you learn in Chem 20. There's different configurations for compounds, and water always configures this way to keep, just based on the electronegativities, essentially. Okay, so what we end up getting is a positive part and a negative part. Now, How many people have ever seen, like, if you put water in a glass and you fill it really slowly, that you can actually fill it just a little more than full, right? You get that meniscus, right? That surface tension. Okay, what causes that? Cohesion. Okay, the stuff, the term for that is cohesion, and cohesion is caused by hydrogen bonds. Hydrogen bonds happen when this water molecule and another water molecule form a weak bond between each other. The positive hydrogen of this water molecule and the negative oxygen of this one create a weak bond between them. Okay, like a meniscus isn't strong, right? If you take your finger and you tap it, it breaks and the water falls, falls over the sides. Okay, it can reform again quickly. But these little hydrogen bonds form because there's a positive and a negative that are attracted to each other, and they'll form a weak bond between them. Okay, that's called cohesion. Now, you may have also seen that if you have a really cold drink, water starts to condense onto the glass on the outside, and those droplets seem to somehow stick till they get to be kind of too big, and then they'll run down the side. But when they're kind of small, they stick to the side of the glass, seeming to defy gravity. Okay? This is the same process, except now it's called adhesion, okay? Because it's water bonding to something else, in this case, the glass. Okay? So if there's another at least somewhat polar molecule around, water can form a hydrogen bond between it and this other molecule. Okay? We call that adhesion because it's a different molecule. Cohesion is water to water. Adhesion is water to something else. Okay? In the end, the process is the same. It's a hydrogen bond between two polar molecules. Okay, everybody kind of follow there? All right. Okay, so this is what we've been talking about here. We talked about the electronegativity already. Okay, polar covalent bonds are ones in which the electrons are not shared equally. And we talked about this hydrogen bonding here. Okay, hydrogen bonding happens when the negative part of an atom, of a molecule, okay, kind of forms a weak bond with the positive part of another molecule. So one water molecule can form 4 hydrogen bonds with other water molecules. There's 2 positive parts on the top where the 2 hydrogens are, and there's 2 negative parts on the bottom. Okay, so it can form 4 bonds, okay, with other molecules. This is what relates to what happens to water when it freezes. Okay, what happens to water when it freezes? It expands, right? Okay, these hydrogen bonds don't like to get squished. Water actually has its smallest volume at around 4 degrees Celsius. You start cooling it below 4 degrees and the water molecules they try to get closer together, but they're repelled. These hydrogen bonds, it's almost like if the hydrogen bonds were made out of something that's a little bit flexible but a little bit elastic, and when you push it together, you can only push it so far before it springs back. Okay, and that spring back happens just as the water is beginning to freeze. Okay, and they push away from each other and then solidify, and the water has expanded now. Okay, because these hydrogen bonds didn't want to be pushed together too much. Okay. All right, so you were asking about the shape. Why does, bless you, yeah, why does water kind of have this shape? Well, it's because we've got this positive here and this positive here. They repel each other, so they have to have a certain distance between them, right? They don't want to go all the way around because the electrons are being held here at the bottom, or top in this case. Okay, so they just always form this right angle. Actually, it's 90-degree angle between them. Okay, now here's our water molecule. We said it could bond to 4 other water molecules. Okay, and that's what creates, again, surface tension, adhesion, cohesion, okay, that kind of thing. Okay, and as we were saying here with water, when it freezes, okay, so this would be water here at about 4 degrees Celsius, liquid water. Okay, the water molecules are about as close together as they're ever going to be. Okay, they can be closer as a liquid because as a liquid, they have the freedom to move past each other. But when water solidifies and crystallizes, okay, those hydrogen bonds force the molecules away, and the water expands. Okay, before it becomes a solid. Okay, so has life on Earth kind of evolved around the properties of water? I mean, is water essentially essential for all life on Earth? for all life as we know it, right? I mean, when we're searching for evidence of life in other places, what are we always looking for? Water, okay? Like, we're very single-minded of purpose about that. We just, who knows if water is really necessary for life? We don't really know that, but we assume it's true because that's all we've ever seen, okay? But water does have these anomalous properties, and life on Earth has evolved to use a lot of those properties. Okay, prime example of that is how trees, or basically any vascular plant, transports water from its roots to its leaves. Okay, that's a long way for some trees to transport water, and it's against gravity. Okay? There's no pump inside a tree, okay, that's just pulling water out of the dirt and going and squishing it up the tree. Okay? It doesn't work that way. And we're going to look at this in more detail in the biology unit, but right now we're going to look at it just from the standpoint of water is polar, and it allows trees to transport it because of that. Okay? So what happens is, inside the little tubes that transport water inside the tree, okay, called the xylem tubes, okay, water, and the xylem tubes are really, really, really small, like they're microscopic. Okay? Each tube is very, very small. Inside of those tubes, water will bond to itself, okay, in cohesion, and to the inside of the tree in adhesion. So the water won't fall back down. Individual molecules will get stuck to the inside of the tree and to each other, right? As long as there's a pulling force from the top of the tree, which there is, okay, then these water molecules won't fall back down, right? But again, the tubes have to be really, really small, all right? Imagine if you had, let's say, like a straw that was, you know, an inch in diameter. Would it be easier or harder to draw liquid up that one than a small one? Harder, yeah, because you have this large column of water that you have to support with the suction you can create. All right, a small straw is much easier because the column of water is smaller and lighter because there's less water in there. Okay, that's why the tubes inside a tree have to be so small. If they were big, the tree wouldn't be able, the hydrogen bonds wouldn't be strong enough to hold that column of water together. They would break and the water would fall back down the tube. The tubes being really small, okay, these hydrogen bonds can hold the water in there. And so what ends up happening is the water molecules are like, how many people ever played with like the barrel of monkeys? Right, the plastic monkeys, right? And you could link their arms together, okay? Well, that's essentially what happens with the water molecules inside of a tree, okay? The links in the arms would be like the hydrogen bonds between the water molecules, okay? And then the monkeys could also, the water molecules could also stick to the inside of the tree. So the tree supports them, they support each other, and as they are evaporated from the leaves, the whole link, the whole chain gets pulled up because they're all still attached, okay? That sort of makes sense? So as water evaporates out of the leaves, it pulls the other water molecules below it because they're all attached by these hydrogen bonds, and that's how water moves up the tree. It's not actively pumped up there, it's actually pulled up by the force of evaporation, evaporating water from the leaves. Okay? But if water wasn't polar, this wouldn't work. Okay?
So it's connected, and as we're leaving the leaves,
right, it pulls the other ones up, exactly. Okay, but if water was not a polar molecule, this would not work. Okay, because it wouldn't be stuck together then. There'd be nothing holding the molecules together. There are, like ammonia is a polar molecule. There's lots of other polar molecules. Water is just the most common one, and it creates kind of the best hydrogen bonds. So we see it, the evidence of it being polar quite a bit more. Okay, so things to remember here. Terminology, cohesion. Okay, so cohesion is when a water molecule forms a hydrogen bond with itself. Okay. Yeah, so hydrogen bonds hold the substance together. Okay, that's cohesion. So cohesion could also be, let's say, water to water. Right? Cohesion means that they're the same molecule. Okay? Adhesion means different molecules. That's why adhesives, okay, glues are called adhesives. They glue things that are not alike together. Okay, so adhesion is things not alike together. Cohesion is things that are alike together. Yeah, adhesion and cohesion are caused by the same thing. They're both caused by hydrogen bonds. It's what's the hydrogen bond between? If it's two water molecules hydrogen bonded, it's cohesion. If it's a water molecule and some other polar molecule, then it's adhesion. But it's still a hydrogen bond in both cases. Okay, so that's one example. Okay, how many people have ever seen, I can't remember what its technical name is, but the people always call it the Jesus lizard, the one that can run across the water. Okay, all right, well, it's using the polar nature of water as well. Okay, because there's surface tension. Okay, the Jesus lizard with its big kind of splayed feet can, and its feet go in this weird like propeller action, okay, across the water, right? And it can do that because there's enough strength in those hydrogen bonds that the lizard won't fall through. Okay, it doesn't. I mean, it breaks them a little bit, but not enough to fall through unless it slows down. Okay? If it slows down, then it'll fall through. Okay, same with skipping a rock. Okay, if you've ever skipped a rock on the water, essentially you're bouncing it off of the cohesive layer of surface tension, okay, that's on the surface. Now, where's the best place to skip a rock? A lake or a river? Yeah, a lake, right? You get that surface tension isn't broken as much in a lake. If it's a windy day, you're not going to be able to skip the rock as well as you can on a calm day because the waves will disrupt the surface tension. They'll break the hydrogen bonds. I mean, they'll come back together, but if they're constantly breaking and coming back together, then it's not as cohesive on the surface and you won't be able to skip rocks as well. Okay, because the surface will be uneven. Same with a river. It's really hard to skip a rock across a river because the river's always moving. Okay, the hydrogen bonds are always breaking. All right, and then adhesion is the clinging of one substance to another. Cohesion, same substance together. Adhesion, different substances. All right, so this is adhesion here, right? You can see that on the surface of a leaf, there's a waxy cuticle on the surface of a leaf, and the water doesn't penetrate that, so it sits on the surface, but it can create a hydrogen bond with that waxy material, and then it'll stick to it, okay, until the drops get too big, and then, of course, the hydrogen bonds aren't strong enough, and it rolls off. If you're stirring it, yes. Dissolving something, not necessarily, but you are going to change the properties. It's not just going to be water anymore. So dissolving something in water will probably change its ability to make those hydrogen bonds with itself. It's also a polar molecule, but it's a barrier to water. That's why we do it, right? It doesn't allow water and whatever else is in the water to penetrate to the paint, right? It's a sacrificial layer that we put on the car. And then, yeah, so water beads up. You can always tell if a car is waxed or not waxed after a rainstorm, okay? If a car has been waxed, then the water beads onto the surface. If it hasn't been waxed, it's a sheen, because it can't create the hydrogen bonds nearly as well and runs off, okay? Whereas if you have the wax, the hydrogen bonds will form, but the water won't penetrate either. Well, it's a little bit of both. It's more just showing that it's not about adhesion, it's more about showing that there's surface tension enough there that you can apparently put a paper clip on it. I tried this for 3 hours one day. 3 hours of my life I'll never get back. Okay? And I was not able to do it. Apparently what I was missing was you have to bend the ends of the paper clip, the sharp ends up, and I didn't do that. Okay, you can see kind of here in this picture that the sharp ends are bent up so they don't break the surface tension of the water. But I don't know, maybe I just needed another cup of coffee, my hands were shaky or whatever, I don't know. Okay, I just couldn't do it. No, it's showing surface tension, which is cohesion. I said it's not showing adhesion. Yeah, this one's showing adhesion here. Well, it's actually showing both as well. I mean, to form a bead like this, there has to be surface tension within the water, but it's adhering to the leaf itself, right? Okay, and then, like I say, we got the Jesus lizard that can run across the surface tension. Okay, you also have things like water striders and other types of flies that might, rest on the surface of the water. Okay, they're not able to break the surface tension, so they can sit on top of the water. Okay, if you got, like a water strider like this, and you drop a rock beside it, it'll sink. Okay, because you'll break the surface tension of the water it was sitting on, and it'll sink down. Okay. Now, if we float on the water, are we using the surface tension? No, we're just using buoyancy. Okay, it's different. To float is different than to actually sit on the water. Okay, to float you have to displace a volume of water equal to your mass. Okay, but to actually sit on the surface film, okay, that's different. That's not floating. That's using the polar nature of water. Okay, we can't do that. We can't just go like this and go, okay, I'm going to sit on the surface tension now. Like we're too big, and the surface tension is not strong enough. You should float on Mercury. You wouldn't be able to walk on it because it wouldn't have surface tension. It's a metal, right? But yeah, if you had enough of it and you weren't worried about being poisoned, you could, like I've actually seen a picture of a billiard ball floating in a glass filled with mercury. So it's floating on top of the metal because the mercury is more dense than the billiard ball is. You can float more easily in the Dead Sea because of all the salt in it. It's not so much about surface tension, it's just that you float easier in salt than fresh. Yeah. That was your question? Probably not. Not that I know of, anyway. Cornstarch doesn't make so much the hydrogen bonds quicker as it creates what's called a colloid. Okay, like cornstarch in water makes a mixture called a colloid, which is a mechanical mixture that creates like a solid object, a semi-solid object. So it's not changing so much the hydrogen bonds as it's changing the chemical nature, physical nature of the material. Not that I can think of off the top of my head. I mean, it's possible, but I don't know. Okay. All right, so that's it for the stuff on polar nature of water and solubility. What you need to be able to do, guys, is the following, okay? On a test, I'm going to ask you, okay, like on your unit exam, I'll ask you about the polar nature of water, okay? What you need to be able to explain to me is, what's a polar molecule? Okay, so in a polar molecule, electrons are not shared equally. Okay, that's the big thing there. Okay, in a polar molecule, electrons are not shared equally. Okay, and that results in that molecule being able to form hydrogen bonds with other molecules like itself or other molecules that are polar. Okay, that would be cohesion and adhesion. So being able to explain those two things and give me an example. I would say probably the transport of water in a plant would be a really good example to use. All right, so those are the things I'm looking for about a polar molecule, to be able to tell me what it is. Okay, talk about cohesion and adhesion, hydrogen bonds causing them, okay, and then an example. Both are in the tree. Cohesion is when the water molecules are linked together. Adhesion is when the water molecule is linked to the inside of the tree. So both occur. Both have to occur for the water to be transported. Okay. That's a good question. I honestly don't know the answer to that. I would think that smaller would be stronger just because there's less area for disruption, but I couldn't tell you for sure. Yeah. Okay. So what I want you guys doing now is working on the other naming things. All right. So again, guys, in the About tab, you're looking for the worksheet package. We've done the first two naming sheets already in class. Okay, so we've done that one. And we've done this one here on naming compounds. Okay, but there's this one here that I want you to start on. So it's on page 6, okay, of the workbook, and there's some more after that as well. Okay, so they've got a mixture here, and I'll put those two, the keys for both of those in the stream in Google Classroom here in a minute. Okay, so you'll have access to those here right away, and then you can check as you go. I'll also put the keys up on the board. No, this says final formula review, write formula for these compounds, and then name these compounds down below that. It's on page 6. Okay, so there's the key for the first one, guys, and I'll scroll it up as need be, but like I say, it'll be in the stream in Google Classroom, right? So you can open it up there as well as a PDF so you can see it on your phones. Okay.